what happens when not just two, but three or more charges come together in a system. How do these multiple charges interact, pushing and pulling each other in the vast expanse of space? Understanding these complex interactions is fundamental to electromagnetism and has wide-ranging applications in various fields of physics and engineering. Today, we'll delve into the fascinating world of electrostatic forces, specifically exploring how to calculate the net force on a single charge when multiple other charges are present in its vicinity. This builds directly upon our foundational understanding of Coulomb's law, which describes the force between just 2-point charges. We will extend that knowledge to more intricate scenarios. Before we tackle the complexities of multiple charges, let's take a moment to quickly recap Coulomb's law. This essential law provides the mathematical framework for describing the electrostatic force that exists between any 2-point charges, laying the groundwork for all our subsequent discussions on multi-charge systems. In the real world, the interactions of multiple charges are not just theoretical constructs, they are ubiquitous. From the intricate dance of electrons within atoms and the formation of complex molecules to the behavior of materials and the design of electronic devices, systems often involve numerous charges interacting simultaneously. These interactions dictate the properties and behaviors of matter at a fundamental level. This brings us to our central and most important question for today. How do we accurately and systematically calculate the net force on a single, specific charge when it's influenced by the combined electrostatic forces exerted by several other charges surrounding it? This is a critical skill for analyzing many physical phenomena. Let's begin our detailed review by revisiting the fundamental principle that governs electrostatic interactions, Coulomb's law. This law, formulated by Charles Augustin de Coulomb in the 18th century, precisely quantifies the magnitude and direction of the electrostatic force between any two stationary, electrically charged particles, often referred to as point charges. The mathematical formulation for Coulomb's law states that the magnitude of the electrostatic force, denoted as F, is directly proportional to the product of the magnitudes of the two charges, Q1 and Q2, and inversely proportional to the square of the distance, R, separating their centers. Specifically, F is equal to K, Coulomb's constant, multiplied by the absolute value of the product of Q1 and Q2, all divided by R squared. This inverse square relationship is a hallmark of many fundamental forces in nature. In this crucial formula, K represents Coulomb's constant, which is a fundamental physical constant in electromagnetism. Its approximate value is 9 times 10 to the power of 9 Newton meters squared per Coulomb squared. This constant accounts for the proportionality between the charges, distance, and the resulting force, and its value is derived from experimental observations. An equally important aspect of Coulomb's law, beyond just the magnitude, is the direction of the force. The electrostatic force always acts precisely along the imaginary straight line that connects the centers of the two interacting charges. This directional property is crucial for correctly applying the law, especially when dealing with multiple charges in vector addition. The nature of this electrostatic force is entirely dependent on the types of charges involved. If the two charges are alike, meaning both are positive or both are negative, they will repel each other, pushing away along the connecting line. Conversely, if the charges are unlike, one positive and one negative, they will attract, pulling towards each other. This fundamental principle of like charges repel, unlike charges attract, is central to understanding all electrostatic interactions. To fully and accurately describe these forces, especially when we move beyond simple two-charge systems and into the realm of multiple charge interactions, we often employ the vector form of Coulomb's law. This advanced form accounts for both the magnitude of the force and its precise direction in three-dimensional space, which is essential for performing vector addition to find net forces. Understanding these foundational principles and nuances of Coulomb's law is absolutely crucial before we can effectively delve into the complexities of multiple charge interactions. A solid grasp of how two charges interact provides the essential building blocks for analyzing more intricate systems where many charges exert forces simultaneously on each other. This recap ensures we have a strong base for the next steps.